Okay, I've got a big egg in my face. All right, let me get all this stuff out of here. Look like you're already a nerd. You don't need to look like it that bad. Anyway, I screwed up on that one problem that I did on Friday, and a few of you have pointed that out to me politely. One of you, the young man who approached me this morning was kind of frustrated. He's like, "Wait a minute, I did this exactly, and it's not even coming close." There was a problem. So let's take a look at this problem. I'm going to go ahead and get my ugly mug off here. By the way, did anybody try and watch at all? I know there's much bigger things, much bigger fish to fry going on in our country right now, but than football, than the NFL. But I've probably watched a grand total of the two championship games that were played. Probably watched a grand total of 45 minutes. It was so dull and it was so one-sided on both games. In fact, all the playoff games were so horrendously boring. The NFL is slow. I'm watching. Basically, ladies and gentlemen, my prediction: you are watching the NFL die before your very eyes, and literally, their players are too. So, all right, that's my editorial comment. People goes, "You're crazy." You know, it's the most popular. Yeah, for right now. But I'll tell you what, the NBA and soccer is. You know, look at the demographics. NBA and soccer are going to be pretty huge. And plus, one of the biggest downfalls that's going to happen to football is that parents of children, the enrollment into little league football leagues is down like 12% each year. That's if you had an investment like that, guess what? Your investment goes to zero. That's an extinction rate. Anyway, all right, and pretty soon high schools and stuff and junior highs, school districts are going to get tired of paying for it. I also think they're going to go, wait, soccer costs this much? Hold on, men and women can play soccer. Anyway, foreign countries think we're crazy. I kind of given you my physics and sport thing here. You don't need to hear all this. Countries think a lot of foreign countries think we're crazy with the amount of money that we spent in our educational system on extracurricular sports. I find that other countries have club things, neighborhood club type things that their kids participate in, and I've seen some softball leagues that are just out of this world as far as being advanced and a little bit. Whoa, that's not the little league I played. But anyway, all right, let me get off here and stay. Let me cut this off if I can. Yeah. I don't know why that didn't work the first. All right, here's the problem. Oh, let me go to the student view. I screwed this up. Egg in my face. Come on, student view, today. Let's make this happen. All right. It is a Go problem, so that's why some of you are probably catching my stupidity on this. And it wasn't stupidity. I'm going to claim the. Oh, I've gone back to my original one. Now, I've done this two ways, and one way I got the right answer, and one way I got the wrong answer, even after I corrected for my initial mistake. Here's the deal. An unrestrained horizontal spring. Let's just draw the picture again. And let me get, so these objects, it's 0.3 meters long, and it's got a K of 200. I'll show you all this in a minute. 200 newtons per meter. And two small objects are attached to the spring, one at each end. The chart, so small meaning they're not going to, they're negligible in mass. Okay, have equal magnitudes. Because of these charges, the spring stretches by 0.3 meters. So my delta X is equal to 0.03 meters. This is not, my delta X is not the same as the distance between the charges. That's how far the springs, this is where I compute my force. So let's take a look at what's going on here. All right, let's just go to the picture. Oop, wrong one. All right, now here we go. So the spring, put my two charges on here. I'm just going to make them both positive so that they've stretched. All right, and this R that I'm going to come up with becomes where I made my mistake earlier. Okay, first of all, to find the force, they were like right here, and now they've stretched to here. All right, let's say they stretched equally on both sides, so they went 0.015 here and 0.015 here, so the total stretch delta x is 0.035, and we know that the force that's holding those apart is 200 times 0.03 meters. Okay, well, this is the same force, so you can go ahead and calculate that, but this is the same force that is equal to, now, hold on, what is R? Well, R is the initial length of the rod was 0.30 meters. Okay, and so you'd calculate whatever this force is, and that looks like it's going to be what? That looks like it's going to be 6, right? 3% of $200 is $6, 6.00 newtons. That's not very much. Okay, and then, now what is the distance R? Well, R is now L plus delta x. And this is the way I calculated it, so that when you find you've determined the force is equal to the new K, which is the electric K. This is the spring constant K up here, and this is the electric K, is equal to 9.00 times 10 to the 9th newtons meters squared per coulomb squared, like that, okay, is equal to Ke times the charge squared, because they're like charges, so it's Q times Q, over L plus delta x and the whole quantity squared. And so F becomes L plus delta, and this is the way I did it, squared. And I tried it with just using this L on, I tried it just using the L, thinking, oh, maybe that little bit of stretch won't make it. It made a huge difference. So use this as your R. That R now is equal to L plus delta x. X squared is equal to Ke times Q squared, and so Q is equal to the square root of F times L plus delta x squared divided by the electric constant. Make sure you get that electric constant in the square root. And that should be your Q. Okay? Sorry about that.